everyone, I'm Dr. Rizwana, working as a Professor of Physics in Institute of Aeronautical Engineering. Today I'm going to do some numerical problems based on phenomena of diffusion and drift occurring in PN junction type. So in my previous videos, I have discussed a lot about formation of PN junction diode, what happens when PN junction is formed, and then after that we have seen how energy level diagram is going to get modified, and then we have seen biasing of PN junction. Now today, so using all those phenomena and of course considering one very important theory, which is classical free electron theory, we'll try to just look into this phenomena of diffusion and drift. So proceeding further, first just we'll try to have a glance at the phenomena of diffusion and drift. But before that, just we'll try to recollect what exactly is PN junction diode, so that it will help us to understand these phenomena better. So when we are talking about this PN junction diode, generally how this PN junction is formed? PN junction is formed when we combine P-type and N-type semiconductors. So if we take P-type and N-type semiconductors and if we combine them, then of course we will get PN junction. And when we talk about these P-type semiconductors, these are extrinsic semiconductors which are formed by doping travalent impurities to intrinsic semiconductors. Similarly, N-type semiconductor, it is formed by doping pentavalent impurities to intrinsic semiconductors, and as a result we know that in P-type semiconductors we have lot of holes, whereas in N-type semiconductors we have lot of electrons. So majority charge carriers in P-type semiconductors are holes and majority charge carriers in N-type semiconductors are electrons. And once we form PN junction, okay, by combining this P-type and N-type semiconductors, then there is one very important phenomena that is taking place here. That phenomena, it is called as diffusion. So that process, it is called as diffusion. And actually when we talk about this diffusion process, just we can have look at this particular figure. So when we talk about this diffusion, what generally we'll observe here is, of course, when we again take this PN junction diode. So this is our P-type semiconductors and these are N-type semiconductors, and this is the junction layer which is separating P-type and N-type semiconductors. And we know that in P-type semiconductors we have majority charge carriers holes, and in N-type semiconductors majority charge carriers are electrons. And once PN junction is formed, we know that in P-type we have higher concentration of holes, whereas in N-type we have very small concentration of holes. So that's why, because there is change in the concentration of charge carriers, so diffusion process takes place. So what exactly is diffusion? Where we have flow of charge carriers from higher concentration to lower concentration. So that's why what we are going to observe here is holes, they'll start moving from P side and they'll enter into the N side. Similarly, electrons from N side, they'll flow towards the P side. So this process of movement or migration of majority charge carriers from higher concentration to lower concentration, that particular process, it is called as diffusion. And once this process of diffusion is taking place, so what we are going to observe here is, of course, here we have holes, and once holes go to N side, they are going to lose their energy. They are going to combine with electrons there and they will become immobile positive ions. So once these holes, when they get migrate to N side, so they are going to become immobile positive ions. Similarly, electrons, when they migrate from N-type semiconductor and when they go to P-type, they are going to lose their energy and they become neutral with the holes and they will become negatively charged ions. And they are going to become negatively charged ions. And what we are going to observe here is, once there is formation of or once there is collection of immobile charge carriers in the region near to this junction layer, of course, where we have immobile positive ions accumulating towards the N side of PN junction, and then we have immobile negative ions getting accumulating near the P side of PN junction. Then once we reach to this equilibrium stage, then what you're going to observe here is these immobile separation of positive and negative ions, it is going to generate electric field. So it is going to generate electric field. And because of this electric field, of course, once there is generation of this electric field, diffusion of charge carriers will stop. So here diffusion of charge carriers will stop, and then next, what we are going to observe here is once electric field is produced, this electric field, it is going to, sir, screen పోయింది సార్, శ్రీకాంత్ వచ్చింది 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 వచ్చింది. So as there is accumulation of immobile positive ions and negative ions in depletion layer, and because of this charge separation, electric field will be produced. And what this electric field will do, this electric field, it is going to oppose for the diffusion process. But what this electric field is going to do, this electric field, it is going to supply energy to these charge carriers to move, and that particular process, and because of this electric field, some of the charge carriers, they will be migrating across the junction, and this migration of charge carriers, because of this electric field, this phenomena, it is called as drifting. So what is drifting? Where charge carriers will gain energy because of external electric field, whereas diffusion, it takes place because of change in concentration of charge carriers. So both these phenomena, they'll occur when we talk about this PN junction level. So just quickly we'll see what exactly is this diffusion process. Now if we can look at this figure, here we have movement. Generally diffusion process is nothing but movement of charge carriers from higher concentration to lower concentration, and thereby generating diffusion current. And this occurs, and generally diffusion takes place when we consider a semiconductor which is doped non-uniformly. Of course, where we are talking about p-type and n-type semiconductors. So when there is non-uniform distribution of carriers in a concentration gradient, then this process of diffusion will take place. And for this diffusion process to take place, that it does not require any external electric field, and generally it depends on the repulsive forces between carriers of same charge that are highly concentrated in an area. So this point is very, very important. So when we consider this process of diffusion, we don't need any external electric field, and this flow of charge carriers, it takes place because of repulsive forces that are there between the charge carriers that are highly concentrated in an area. And what we are going to observe here is this initial carrier concentrations. So like generally charge carriers, they are going to move from higher concentration to lower concentration, and this concentration region, it is going to determine the direction of diffusion current. So here generally the current moves to the direction where there is initially higher concentration of electrons or lower concentration of holes. So generally we'll take this diffusion current direction from higher concentration region of current. From there they'll go to, of course, lower concentration, or we'll consider the region where we have lower concentration of the holes. So it means that simply current moves in the same direction as the movement of holes and opposite to that of electrons. So that we can make out in the figure which is shown in this particular slide. So as you can make out that here we have, of course, this is near the depletion layer. So here we have this positive ions, these are negative ions. So we have our current. As you can make out that current due to diffusion of electrons, it will be opposite to the movement of the electrons, whereas diffusion of holes. So here the current produced because of holes, it will be in the same direction as movement of the holes. And because here these charge carriers, they are diffusing from areas of higher concentration to areas of lower concentration, then generally what we'll do here is, when we talk about the sign, we'll use plus q sign for electrons, whereas minus q sign, it is used for holes. Now coming to drifting process, of course, when we talk about this drifting phenomena, as you can see here, so drift current arises from the movement of carriers but under the influence of electric field. So when we apply electric field, under the influence of electric field, drift current will arise. And here positive carriers, which are nothing but the holes, they move in the same direction as electric field, whereas the negative carriers, they move in the opposite direction. So this is very important case. So as you can make out in this figure, of course, we are applying electric field in this direction. Then all the holes, as you can make out that holes, they started moving in the direction same as electric field, whereas electrons, they'll start moving in the direction opposite to the electric field. And this current, which is produced because of movement of charge carriers under the influence of electric field, is nothing but drifting. And whatever this net motion of charge particles, it is going to generate drift current, and this drift current direction, it will be same as the applied electric field. And here what there is one term, drift velocity. So this is the velocity gained by charge carriers under the influence of externally applied electric field, where charge carriers are forced to move under the action of electric field, and it contributes to mobility or movement of charge carriers under the application of electric field. So this drift velocity and mobility, it takes place only under the action of external electric field, and whatever drift current we are getting, it is going to follow Ohm's law, and we know what is Ohm's law, where voltage is proportional to current. So V is equal to IR, it is Ohm's law, and this law, it is going to be followed by the current which is produced because of drifting of charge carriers. And as I told you that this drifting process, it is mainly influenced by external field and as well as charge carrier concentration. So this is about the two phenomena, diffusion and drifting in PN junction diode. Now, as you can see here, so of course when we talk about diffusion, drifting and all those processes, so these processes, they are also related to one important theory, okay, which is proposed by taking into consideration metals. So that theory, this is called as classical theory also, and this theory, it is called as classical free electron theory of metals. So generally it is taken as classical free electron theory of metals. And here mainly it helps us to understand why metals are good conductors of electricity. But this, when we try to explain other properties exhibited by solids like being an insulator or semiconductor, this classical free electron theory is going to fail. But right now, considering this classical free electron theory and also by considering the phenomena of diffusion and drifting, so we'll try to take some terms, very important terms, and using those terms, we are going to solve some of the numerical problems. So here, when just before that, quickly we'll try to have a glance about what exactly is classical free electron theory. And we know that this classical free electron theory, it was proposed first by Drude. So by scientist Drude, and it was done in year 1900. And as I told you, of course, later it was developed and it has been extended by another scientist, Lorentz. So that's why this classical free electron theory is also called as Lorentz-Drude theory. And mainly it explains about electrical conduction in metals. And when we talk about a metal, we know that generally if we consider atoms of the metal, we know that there are plenty of electrons simply wandering from one atom to another atom. So if I consider here, generally when we try to express metal, so we'll take positive core, and this positive core, it is surrounded by its valence electrons. Similarly, if I go to other atom, here also I'll have positive core surrounded by its valence electrons. So like this. So when we talk about a metal, so here we have array of positive ions. If I take metal crystal, then I'll have array of positive ions which are separated by one constant distance, which is called as intra-ionic distance. And coming to these valence electrons of each atom, they are not just fixed to that atom, but they keep on wandering from one atom to another atom. So here, as you can see here is valence electrons of metallic atoms, they are free to move in the spaces between ions from one place to another place within metallic specimen. And here, the very important assumption made by Lorentz and Drude is they are just comparing these free electrons in metals to molecules of gas. So this is very important concept given by classical free electron theory. So they are just comparing free electrons in a metal with molecules of gas, and we know that when we take gas molecules atoms, they are very free to move away in all possible directions, and they are far away from each other. They are not bounded to each other. So they'll be freely moving, and as I told you that they'll be moving in all possible directions with all possible velocities. And when we consider such gas molecules, when they are moving, they will collide with each other also. So they'll be colliding with each other, there'll be exchange of energy. Similarly, like molecules of gas, here also free electrons belonging to metal. So they are not just fixed to one atom, but they'll come out of one atom and they'll keep on moving from one atom to another atom. So they are treated as electron gas, free electron gas. So electrons associated with metals, they are treated as, they are considered as free electron gas. And of course, these electrons, they are giving high electrical conductivity of metals. So these electrons are also called as conduction electrons. But as you can see, when we talk about the molecules of gas, we talk about some interaction. But actually, there is no interaction between conduction electrons. And even these electrons' interaction with these positive ions is also very, very negligible. And these free electrons, they'll find uniform electric field of positive. So what is the role of positive ion? It is going to impart uniform electric field. So when we have such gas molecule, when we have such free electrons behaving as gas molecules moving randomly in all possible directions, so there are some terms related to such free electrons. So first term is mean collision time. So this is called as mean collision time, and it is represented by notation tau. And how it is defined? It is defined as average duration of time that elapses between two successive collisions. It is called as mean collision time. So we know that when we take electrons, because these electrons, they are moving in all possible directions, of course they will be colliding with each other. So they are colliding, but generally we'll say that there is no interaction between them. And generally, when these electrons are going, they'll go and collide with the adjacent electrons. So what is the duration taken between two successive collisions? That is nothing but mean collision time. And when we try to get its mathematical expression, this relaxation time, it is taken as ratio of lambda by c. What is lambda? Lambda, it is called as mean free path, and c, it is called as root mean square velocity. Because here, why we have to talk about root mean square velocity? Because we know that they are not moving in one possible direction, they are moving randomly in all possible directions with all possible velocities. So that's why if you want to consider velocity, then we'll just take root mean square velocity. And what exactly is mean free path? Just we'll try to see in the further definitions, but before that, we'll talk about mobility mu. So here, suppose I have such free electrons, and to those free electrons, if I apply electric field, so first I have randomly moving electrons, and to such randomly moving electrons, when we apply electric field, all these electrons, they start moving in one particular direction. So they'll gain velocity in one particular direction. So that velocity, it is called as drift velocity. So that particular term, it is called as drift velocity, and it is generally represented by Vd. So what is Vd? Vd is velocity gained by electrons in one particular direction on application of electric field. And this mobility, this movement of charge carriers under the application of electric field, it is called as mobility of charge carrier. So what is mobility? It is taken as drift velocity of charge carriers per unit electric field. Now coming to next term, relaxation time of electrons. So we know that previously we were talking about mean collision time, but when we talk about this relaxation time, which is represented by tau r, so how it is defined? It is defined as average value of time elapsed after the last collision of all the electrons in a perturbed system has taken place. Or we can also say that it is defined as duration of time required for an electron to decay its drift velocity to 1 by e times of its initial velocity. So actually, mean collision time is how much time is taken between two successive collisions. But when we talk about relaxation time, time taken. So suppose if I try to draw one graph by taking time on x-axis and then drift velocity on y-axis. Suppose this is my initial time where it is moving with drift velocity Vd. But as time goes on, then what happens to its drift velocity? It keeps on decreasing. And generally, we'll consider one time. That time we are taking it as tau r. And what happens at this? Suppose if this is a drift velocity value Vd, and at this tau r, what happens to drift velocity? It's decreased by 1 by e times its value, its initial velocity value. So that is nothing but relaxation time of electrons. Then coming to last term, just now we have seen that when we need to define This mean collision time we are taking in terms of mean free path. So what exactly is mean free path? So we know that these electrons, when they are behaving as gas molecules, they'll be moving in all possible directions. So here, what is the average distance traveled by an electron between two successive collisions? Suppose I have one electron, it goes and collide with one electron, and then again this electron going and colliding with another electron. So what is the time taken by an electron between two successive collision is nothing but distance traveled by an electron between two successive collision is nothing but mean free path. And already we have taken this relation. So here, in order to know mean free path, we should know collision time, or in order to find collision time, we should know our mean free path. And of course, C is our root mean square velocity. So by taking all these into consideration, we'll try to take some of the problems based on these terms. Now coming to our first numerical problem. So if you look at this problem, what is the data given? Here we are talking about copper, and for copper, what is the data given? Here data given is density. We were given value of density. And what is the value of density given? Density, it is given as 8.92 into 10 to the power of 3 kilogram per meter cube. So density value, it is given in MKS system. And what is the value? So actually this should be 10 to the power of 3. So 10 to the power of 3 kilogram per meter cube. And whereas coming to resistivity value, it is given as 1.73 into 10 to the power of 8. Coming to resistivity, what is the unit for resistivity? Ohm meter. And also we were given atomic weight of copper. What is the atomic weight of copper? It is 63.5 kilograms. And from this data, we are supposed to find what is the mobility as well as average time collision or mean collision time tau of electrons in copper. So if we just try to see what is the data given, first I was given value of density, and here just in case in order to not to get confused between notation for density as well as resistivity. So density here I am taking it as, or I am representing it by small d. And what is the value of density? Density it is taken as 8.92 into 10 power of 3 kilogram per meter cube. Also we were given value of resistivity. What is the resistivity of copper? It is taken as 1.73 into 10 power of 8 ohm meter. And also we were given atomic weight value, which is 63.5 kilograms. So by using all this data, so and of course we need to find mobility of electrons as well as we need to find mean collision time. Okay, mobility is the drift velocity per unit electric field, whereas mean collision time, we know that it is the average time taken between two successive collisions. So in order to find this, first what we are going to do, first I'll try to find what is the carrier concentration or concentration of electrons in copper. And we know that carrier concentration, it is given by this formula. Carrier concentration, it is equal to Avogadro's number into density divided by atomic weight. So this is one of the important formula. So here we know value of Avogadro's number. Avogadro's number, it is given as 6.023 into 10 to the power of 23 atoms or molecules per mole. Okay, and of course we were given density. So actually because this is in MK system, we can also just like Avogadro's number, we'll take it as 10 to the power of 26. And what is the value of density? Density it is taken as 8.92 into 10 to the power of 3, which is already given, divided by what is the value of atomic weight? It is 63.5. And when we simplify, so what is the value of carrier concentration we are getting? Carrier concentration, so it comes out to be concentration of copper, concentration of electrons in copper, it comes out to be N is equal to 8.46 into 10 power of 25 electrons per unit volume, that is nothing but per meter cube. Okay, now once I know this carrier concentration, and of course I have data for resistivity, I think it will be easy for me to find what is the electrical conductivity of copper. So electrical conductivity, we know that it is inversely related to resistivity. And when we consider such relation, so resistivity is how much? It is given as 1.73 into 10 power of 8. So when we just take 1 divided by 1.73 into 10 power of 8, we'll have our conductivity as 5.78 into 10 power of minus 9 ohm inverse meter inverse. So this is the unit for conductivity. So we have value of carrier concentration. Also we have value of conductivity. Now this is very important relation. Here we are coming across very important relation. And if you look at this relation, sigma refers to conductivity, N is our carrier concentration, and of course E is charge of electron, and tau. When we talk about this tau, tau is mean collision time, and of course M. So when we talk about this M here, okay, so here we have our M. Then of course when we try to get this formula for mean collision time, if we rearrange the terms, it is given as sigma M by NE square. And of course here M is nothing but our mass of electron. So M refers to mass of electron. So when we try to substitute all those values in this definition for tau, so tau it is given as this conductivity sigma into mass of electron divided by carrier concentration into square of charge of electron. So here sigma conductivity, already we got this value as 5.78 into 10 power of minus 9 ohm inverse meter inverse, and coming to mass of electron, it is 9.11 into 10 power of minus 31 kilograms. And then what is the value of this carrier concentration? It is 8.46 into 10 power of 25 into what is the charge of electron? 1.6 into 10 power of minus 19 whole square. And when we try to simplify all these terms, so what is the value of mean collision time? It comes out to be 2.38 into 10 power of minus 27 seconds. So unit will be seconds because we are talking about mean collision time. And what else we need to find? We need to find mobility. So this mobility, of course, we have one very important formula. Generally, conductivity, it is taken as Ne mu, where N is carrier concentration, E is charge of electron, mu is mobility. So from this, how can we get mobility? Sigma by Ne. This is another formula for mobility apart from the formula which I have told you during the discussion of definitions. So it is drift velocity per unit electric field applied. So here already we have value of conductivity, which is 1.78 into 10 power of minus 9 divided by carrier concentration is 8.46 into 10 power of 25 into what is the charge? 1.6 into 10 power of minus 19. And once we simplify, what is the value of mobility? It comes out to be 4.27 into 10 to the power of minus 16. And coming to units, what is the unit? Meter square per volt second. So units for mobility is meter square per volt second. Then coming to second problem, here we are our material under consideration is silver, and to this silver we are given what is the resistivity of silver. Resistivity of silver, it is given as 1.54 into 10 power of minus 8 ohm meter. And also apart from that, we were given electric field. So how much electric field is there along the wire? That electric field value is 1 volt per centimeter. But here resistivity, it is given in terms of meters. So we are going to convert this electric field in meters. So when we convert, because we know that 1 centimeter is 10 to the power of minus 2 meters. So after conversion, what is the value of electric field? It will become 100 volts per meter. And apart from that, we were given value of this conduction electron. So carrier concentration is given. So how many number of electrons are present? 5.8 into 10 power of 28 electrons per unit volume of material. And here we have to calculate two things. Okay, one is drift velocity and second one is mobility of charge carriers. So here from the data given, we were given value of rho, resistivity, and then we have our electric field, and then we have our carrier concentration. So here first we'll try to find mobility, because from the data given it is easy to find mobility first. For that we'll make use of this expression where conductivity it is given as Ne mu, and from this what is our mobility? Mobility it is given as sigma by Ne. And this can also be written as Ne rho, where rho is density. And here we know the value of carrier concentration. It is given as 5.8 into 10 to the power of 28 into What is the charge of electron? 1.6 into 10 power of minus 19. And what is the value of resistivity given? It is given as 1.54 into 10 to the power of minus 8. So here, so when we calculate, so this mobility value, when we simplify it, it comes out to be 6.9973 into 10 power of minus 3 meter square per volt second. Now this is the value of mobility, but what else we need to find? We need to find the value of drift velocity. For that, I'll make use of formula for mobility in terms of drift velocity, which is given as drift velocity per unit electric field. And from this, what is the value of drift velocity? It is simply product of mobility into electric field. Just now we got mobility value, which is 6.997 into 10 power of minus 3 into what is the value of electric field? 100 volts per meter. And when we simplify, so what is the value of drift velocity? 0.699 meter per second. Then coming to third problem. Here in this problem, of course, here we need to find value of drift velocity. And what is the data given? We were given value of current density. So here, we were given value of current density, and generally current density it is represented by J. And what is the value of course here, of course he's asking about the current density in a wire whose diameter is 0.16 centimeter, and how much current is being passed through that particular wire. It is around 10 amps. So what is the data given? Here actually data is the dimension of this particular wire is given, and in this case we were given value of diameter, which is 0.16 centimeter. Now from this I think we can find radius of wire, which is half of diameter, which is d by 2. So this is 0.16 divided by 2, so it comes out to be 0.8. Okay, so here 0.0 this comes out to be 0.8, right? So here in this case, so this is 8, so 16. So here 0.08. So this radius it comes out to be 0.08. So in this case, of course, apart from that, we were also given value of current, and we need to find drift velocity, and also we need to find current density. And also apart from that, we were given value of carrier concentration. So we can find first current density simply by making use of this formula. Current density is simply current per unit cross-sectional area. And what is the current given? Current given is 10 amps, and cross-sectional area is nothing but pi r square. So which is 10 divided by pi value, if we consider it to be 3.14 into what is the radius? Radius, of course, 0.08, but this radius it is in centimeters, so 10 power of minus 2 whole square. So when we simplify, what is the value of current density we are getting? We are getting it as 4.976 into 10 to the power of 6 ampere per meter square. Ampere per meter square. Now we need to find drift velocity. So for that, now we are coming across new formula. So there is relation between current density and drift velocity. So current density is generally given as NE into drift velocity. So from this, how can I get my drift velocity? It is simply ratio of current density to the product of carrier concentration into charge of electron. So what is the value of current density? We got 976 into 10 to the power of 6 divided by what is the value of carrier concentration? It is 8.46 into 10 to the power of 28 into 1.6 into 10 power of minus 19. And if we do it, our value it comes out to be 3.67 into 10 to the power of minus 4 meter per second. The next problem. Here, of course, we are talking about again silver. We were given value of resistivity of silver. So what is the value of resistivity of silver? It is 1.6 into 10 power of minus 8 ohm meter. And also we were given effective number of conduction electron. So here we were given how many number of electrons are present per atom. So here how many number of electrons? 0.9. And also we were given value of Fermi energy EF, which is 5.5 electron volts. And from this data, what we need to find? We need to find mean free path, as well as we need to find relaxation time, electronic relaxation time, and of course drift velocity. when we apply electric field, and what is the value of electric field being applied? It is 100 volt per meter. And apart from that, we were given density of silver, and of course here ratio of mass of electron to its effective mass, it is taken out to be 1. So here first, of course, we are given resistivity value. We can find conductivity simply by taking inverse of resistivity, which is 1 divided by 1.6 into 10 power minus 8. And when we simplify, then this conductivity, it comes out to be 6.25 into 10 to the power of 7 ohm inverse meter inverse. Now I think already we know formula for carrier concentration from the data of Avogadro's number, density as well as atomic weight. So what is the value of Avogadro's number? 6.023 into 10 power of 23. And what is the value of density? It is 1.05 into 10 to the power of 4 kilogram per meter cube. And coming to atomic weight of silver, it is 107.9. And when we simplify it, this carrier concentration, it comes out to be 5.86 into 10 power of 25 electrons per meter cube. Now first we'll try to find relaxation time. So from the data given, we can find relaxation time using formula sigma m by ne square. Conductivity we have calculated, which is 6.25 into 10 power of 7 into what is the mass of electron? 9.1 into 10 power of minus 31. And then coming to this carrier concentration, 5.86 into 10 power of 25 into what is the, of course, charge is 1.6 into 10 power of minus 19 whole square. If we simplify, relaxation time comes out to be 3.79 into 10 power of minus 11 seconds. And we need to find free path. We know that there is a relation between free path and as well as this mean collision time. So mean free path, it is taken as product of this c, which is velocity, or we can take it to be the velocity of light into tau. Tau is mean collision time, and we know that velocity is 3 into 10 power of 8 meters per second, and just now we have calculated relaxation time. So if we simplify mean free path, it comes out to be 1.134 into 10 power of minus 3 meters. And then of course we need to find drift velocity. And in order to find drift velocity, first I'll try to find current density. And for current density, this is our formula. J is equal to sigma E. So conductivity already we have calculated, and we know how much electric field is being applied. So if we take product of conductivity into electric field, this is our current density. Once we know current density, easily we can find drift velocity by using this formula, which is ratio of the current density in the numerator, and in the denominator we have product of carrier concentration into charge of electron. So once we substitute our drift velocity, it comes out to be 0.666 into 10 to the power of 2 meters per second. Now coming to next problem, in this case we were given density of a density of electrons in a conducting rod, and we are supposed to find its resistivity at room temperature as well as its mobility. And here we were given value of collision time. And what is the value of collision time given? It is 2 into 10 power of minus 14 seconds. So coming to the data given, so this is our carrier concentration, which is 8.5 into 10 power of 28 electrons per meter cube. Next we have collision time, which is 2 into 10 power of minus 14 seconds. So first we'll try to find conductivity using this formula, which is Ne square tau by m. We have value of n, we have value of charge of electron, we know value of collision time. So here we were given collision time, which is 2 into 10 power of minus 14 seconds. And then we have our mass of electron. So when we substitute all this conductivity, it comes out to be 4.77 into 10 to the power of 7 ohm inverse meter inverse. And once we know conductivity, easily we can find resistivity by taking reciprocal of conductivity. So when we do it, that resistivity, it comes out to be 2.09 into 10 power of minus 8 ohm meter. Then once we know, of course, resistivity and this conductivity, so it is easy to find resistivity as well as mobility. For finding mobility, of course, we have this formula sigma by Ne. So this conductivity is 4.77 into 10 power of 7 divided by carrier concentration is 8.5 into 10 power of 28, and coming to charge 1.6 into 10 power of minus 19. And when we simplify mobility, it comes out to be 3.512 into 10 power of minus 3 meters squared per whole second. Now next one is a very simple problem. So here we have we need to find drift velocity here. Of course, we were given value of mobility, and our material under consideration is copper, and also we were given value of electric field strength. For that very simple formula where mobility it is given as drift velocity per electric field applied. So from this obviously drift velocity will be product of mobility into electric field, and mobility it is given as 3.5 into 10 power of minus 3. Already it is in MK system, and also we were given electric field in MK system also, which is 0.5. And when we simplify, it comes out to be 1.75 into 10 power of minus 3 meters per second. Then we have our next problem. So coming to our next problem here. So here, when we talk about this next problem, so coming to our next seventh problem. Now, find the, here in the problem given, we have to find here also mean collision time. So we need to find mean collision time, and what is given here, we were given value of here mobility of electron. So what is the value of mobility of electron? It is 3 into 10 to the power of 3 meters square per volt second. And we were given value, of course we know the value of charge, and here we were given mass. So mass of electron, which is 9.1 into 10 power of minus 31 kilograms. And we need to find mean collision time. So this is the value of mobility given, we were given charge of electron, we were given mass of electron. So before finding mobility, okay, so first of course from the data given from mobility as well as mass as well as charge of electron, first in order to find mean collision time, first we'll try to take this formula for conductivity, and this conductivity it is given as Ne square tau by m. And from this, what is our collision time? Collision time is m into sigma divided by Ne square. But when we talk about this mobility, so we have this formula for mobility. Mobility is simply sigma by Ne. So if this sigma by Ne, if I replace it with mu, then this mean collision time, it can be written as m by E into mu. Mass is 9.1 into 10 power of minus 31 into mobility is 3 into 10 to the power of, I think it is minus 3, divided by charge is 1.6 into 10 power of minus 19, and when we calculate it comes out to be 17.06 into 10 power of minus 15 second. Then coming to our last problem, here we were given a copper wire, and of course we were given dimension of copper wire, we were given area. So what is the area? 1 millimeter, we have to convert it into meters. So 1 mm is 10 power of minus 3 meters. And apart from that, we were given how much current is being like flown into that wire. So coming to that current is 10 amp of current. And here we were given, of course, the density of electrons, which is 8.5 into 10 power of 28 electrons per meter cube. And we need to find drift velocity. So in order to find drift velocity, our first step is to find current density. And how to find current density? Simply current per unit cross-sectional area. Current is given as 10. Area is 1 mm square. So here if we try to get it in, of course, in meter square, so it will be 1 into 10 power of minus 3 whole square. So 10 power of minus 6, and if we simplify, it comes out to be this value. And apart from this, next is we need to find value of drift velocity. So what is the relation between drift velocity and current density? So Vd is equal to J by Ne. If we substitute our final velocity, drift velocity, it comes out to be 7.353 into 10 power of minus 7 meters per second. So in this video, we have seen phenomena of diffusion and drifting, and based on this process, there are some terms related to this movement of charge carriers. And of course, for this we have taken into consideration classical free electron theory, and we try to solve problems based on mean free path, mean collision time, then drift velocity, mobility by considering electrons in a metal as free electron gas cell. So with this, I'm going to end my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.